Okay, Chapter 3, Section 6, Related Rates. In this section, we're going to be dealing with a lot of word problems. So it's a really tough section to work through, but I'll do several examples and hopefully you'll get the general sort of pattern that we follow to be able to do these. So for starters, why related rates? So why related rates? Say a university student is concerned that the rate of their increase in financial aid is lagging behind the increased cost of tuition and fees. So that could be a scenario we're trying to study. Or perhaps a renter is concerned that his rent is increasing faster than his take home pay, right? Again, that could be a situation we're trying to analyze. An automobile manufacturer wants to predict how much an expected increase in cost loan interest rates will decrease her rate of sales, right? So as the interest rate for the loans increases, it becomes more and more expensive for the consumers to purchase the car. And therefore, many of them are going to choose not to buy it, or maybe they just can't afford to buy it anymore and they can't get that loan, right? So as interest rates increase, for loans of cars, we could expect that the sales will decrease, and we want to study that relationship. In general, it makes sense, but more specifically, let's put some numbers to that. What kind of sales decrease can she expect when interest rates go up by 0.1%? How does that translate directly to the sales? Or another example, union workers are concerned that the rate of increase in their wages is falling behind the rate of increase of the company's profits, right? So ideally, if the company is making more and more money, their profits are increasing. Hopefully, they're sharing a proportional a proportion of that profit with their employees. So that could be again something that we want to analyze, and this could be something that the union workers can use to negotiate a future contract, right? If they identify that, hey, the company's making a lot of money, a lot of profit, and a lot of that is based on our work as the employees of this company. They have a mathematical argument to make that they deserve higher wages. Okay. All right, so what do all these things have in common? So in each of these situations, there are two quantities that are changing with respect to time. The study of related rates provides a method for determining the precise relationship between the rate of increase or decrease of two quantities. Okay, so in every one of the cases we're going to look at, we're going to have a variable, or we're going to have a quantity that we want to examine. That quantity could be the volume of a liquid. It could be the cost of an item, or the number of items sold. It could be the height of somebody. It could be the length of a shadow. It could be a variety of things, right? That's what makes this section so hard, that the word problems can really come at you from different directions. So there'd be a lot of variety of quantities we might be working with, okay? So you will have some quantities that we want to analyze, whatever they may be. And then also we want to take into consideration how those quantities are changing. So look out for keywords that are the way it changes, right? So we could have the distance and then the way the distance is changing. So the instantaneous velocity, the instantaneous change, how it changes, how it moves, how it increases, how it decreases, right? So those are all keywords. In business, of course, marginal is another keyword. The marginal cost, marginal profit, marginal revenue, right? How is the revenue changing? How is the revenue increasing or decreasing, right? So these are all keywords that we use to represent the derivative, right? The derivative is the instantaneous rate of change of the underlying function. Okay, I know that's a lot, so let's just dive into some examples. So this first example will involve distances and two rates of velocities. Remember that the first derivative of a distance function is speed. The second derivative of a distance function is acceleration. So let's dive into it. So let's say we have this situation. A 26-foot ladder is leaned against a wall. The ladder slips as the top of the ladder begins to slide down the wall. As that happens, the bottom of the ladder slides along the floor away from the wall. As the ladder falls, the distance from the top of the ladder and the distance from the wall to the bottom of the ladder are both changing. Okay, so if the top of the ladder slides down the wall at 2 feet per second, that's a speed, right? 2 feet per second. That's a rate of change. At what rate is the bottom of the ladder moving away from the wall when the bottom of the ladder is 10 feet away from the wall? Okay, so first thing, read the question once, think about it, read it again. They're all going to be really confusing. These are really hard word problems. So it takes at least twice, maybe 3 times to read it through and really think about all the moving parts. Next, come up with a nice little drawing, a little sketch that kind of connects these variables, identify what are constants, what are variables, what are they giving you, what are they asking for. So here's a great little drawing to represent this word problem. So we have a 26-foot ladder. Notice that that's a constant value, right? The actual length of the ladder is not going to change. So 26 is a constant. And then we have the distance from the top of the ladder all the way down to the floor along the wall, right? We can label that y. It's just an arbitrary selection of the variables. You can use a and b, y and x, or something more representative like w for wall and f for floor, right? Whatever you like. But of course, people love x and y in algebra, so it makes sense that we can think of this as sort of the coordinate axes, and we have a y-axis and an x-axis, so it makes sense to use y and x as well. Okay, so let's reread this problem. A 26-foot ladder is leaning against the wall. The ladder slips, and the top of the ladder begins to slide down the wall. As that happens, the bottom of the ladder slides along the floor away from the wall. As the ladder falls, the distance from the floor to the top of the ladder and the distance from the wall to the bottom of the ladder are both changing. Okay, so we have a couple of areas. We have the variable y to represent this distance along the wall, the height from the top of the ladder all the way down to the bottom of the floor. But then we also have a speed in which it is changing, right? So that's going to be the instantaneous rate of change of the y variable. And then we also have the x, which is the distance from the bottom of the wall all the way to the bottom of the ladder along the floor. That's the x distance. And then we have the way it's changing, right? How fast is it moving? As it slides, I think if you can kind of picture this sliding, it probably slides kind of slowly at first. And then as it kind of builds momentum, it starts to slide faster and faster, and then really, really fast. And then just kind of like, by the time it gets to here, the ladder just kind of falls to the floor. So we can imagine that speed, the velocity at which a little dot at the top of this ladder is moving begins slowly to change, but then faster and faster and faster, and then it collapses all the way to the ground. Okay, so now if the top of the ladder slides down the wall at 2 feet per second, at what rate is the bottom of the ladder moving away from the wall when the bottom of the ladder is 10 feet away from the wall? Okay, so what we need to do is come up with an equation that brings together the variables that we're working with. And as this picture implies, this makes a perfectly right triangle. So we know that we can use the Pythagorean theorem. So by the Pythagorean theorem, we know that the y variable squared plus the x variable squared is equal to the 26 squared. Okay, now we're talking about speed, so that's the way an object is moving. Distance traveled over time elapsed. Distance over time is speed, the way something is changing. So we need to take a derivative with respect to time. So we're going to take the derivative with respect to time. That's a very, very common derivative to take in many of these word problems. It's not always going to be with respect to time, so you have to be careful. That's what makes this section really hard. There isn't one straightforward rule that we always use. But with respect to time is a very popular derivative that we have to apply. So let's take the derivative with respect to time of this equation, x squared equals the derivative with respect to time of this side. And, well, let's distribute this. So this is the derivative with respect to time of y squared plus the derivative with respect to time of x squared equals, well, the derivative with respect to time of 26 squared, this is just some constant. It's a big number, but it's a constant. And so we know its derivative is just going to be 0. So let's just simplify that right away. It equals 0. And now the derivative with respect to time of the variable y squared, we know through implicit differentiation that this is going to be equal to 2y and then dy dt plus, and now again with from implicit differentiation, we know that this is going to be equal to 2x and then dx dt equals 0. So now we have a new equation. Here we had an equation that involved just the distance y, the distance x, and the distance of the ladder. So we had that. And now we have a new equation that involves the distance y, the distance x, but also the rate dy dt, the way that the y variable is changing. And we also have dx dt, the way the x variable is changing. How the x variable is changing, how the y variable is changing. The speed of the y variable, the speed of the x variable. So let's read this last part again and figure out what they're giving us and what they're asking for. So if the top of the ladder slides down the wall at 2 feet per second, that's a speed for the y variable. So this is the dy dt variable. At what rate is the bottom of the ladder moving away from the wall when the bottom of the ladder is 10 feet away from the wall? So when x equals to 10, right? That's what this is saying. So this is when x equals to 10. They want to know what is the rate of the bottom of the ladder moving. Okay, so dx dt is the question mark. That's what they want to know. And dy dt is what they gave us. Dy dt. They gave us an indication of how the y variable is changing with respect to time. They want to know how is the x variable changing with respect to time. And this is at a point when x equals to 10. Good. Okay, well, this is what they want to know. This one they gave me. This one they gave me. And, well, we don't know what this is. So what we want to do first, step 1, is figure out what this y value is at this point in time. When x is equal to 10, what is y? So we can plug it into here and solve for our variable. Okay, so let's use this formula right over here. We're going to use this, and we're going to say y squared plus 10 squared equals to 26 squared. So y squared So y squared equals to 26 squared minus 10 squared. And so y equals to plus or minus the square root of 26 squared minus 10 squared. Now it's plus or minus because when we take the square root of both sides, we get a plus or minus. But we know that in this case, the y can't be a negative. So we'll just have to adjust for that. So 26 to the power of 2 minus 10 to the power of 2. Enter. And we want the square root of that. The square root of the previous answer gives you 24. So y equals to 24. So y equals to plus or minus 24. from the math, but we know from our picture that y can't be a negative, right? Y is a distance, so we don't want the distance to be negative. So we're going to ignore the negative. Ignore the negative. And so y equals to 24. Y equals to 24. Okay, so now going back to this formula here, this is what I want to know. I want to know the dx dt. So I'm going to subtract dy, 2y times dy dt from both sides of the equal sign. And I'm going to get that 2x times dx. You know what? Actually, let me organize this a little bit better. Okay, so now going back to our equation, 2y and then dy dt plus 2x and dx dt equals 0, right? So going back to this equation here, this is what they wanted us to figure out right here. Now we know that the y equals to 24 when x equals to 10, and they gave us the value of dy dt. So let's solve for dx dt. I'm going to subtract 2y times dy dt from both sides of the equal sign. And so we get 2x times dx dt equals to negative 2y dy dt. And so now if we divide everything by 2x, we'll get that dx dt is equal to negative 2y dy dt divided by 2x. So now, of course, the 2's can reduce. And we have that dx dt is equal to negative y dy dt all over x. So dx dt is going to be equal to negative 24, that's what the y is, times the dy dt. Now, we said dy dt is this ratio over here. Zoom out a little bit. The top of the ladder slides down the wall at 2 feet per second. Now, since this is kind of like our axis coordinate, usually we have 1 unit, 2 unit, 3 unit, right? So in this direction, it's increasing. And then in this direction, going up is usually positive, right? So we have like 1 unit, 2 unit, 3 unit, 4 unit, right? So going up is positive. Therefore, because this is coming down, we're going to say that the change is decreasing, right? In other words, it used to be, where did it start? It used to be 24 feet high, and then it's going to go to 23 feet, and then 22 feet, right, as it slides down. So this value is decreasing. So we say that dy dt is going to be negative 2. Right? That's important to note, that there is the sign does matter. Okay? The y variable is getting smaller, right? Using the normal, using the scale that this is 0, and then we have 1 foot, 2 feet, 3 feet, right? So it's increasing this way, and so the y variable is coming down, it's decreasing. Good. Okay, so that means that coming back over here, the dy dt will be negative 2 divided by, and then the x, they told us x was 10. So we have everything we need now, and so dx dt is going to be equal to negative 24 times negative 2, which equals to positive 48 divided by 10, which is just going to be equal to 4.8. 4.8. Okay, and so that's the way the x is changing. The x variable is changing. So if the top of the ladder slides down the wall at 2 feet per second, then the bottom of the ladder is moving away from the wall at 4.8 feet per second. Okay, so bringing it all together, we have this ladder. Its length is 26 feet. That's constant. It's leaning up against the wall. It's sliding down. And because the y variable is decreasing, we know that dy dt is negative. Okay, so the question was, if the top of the ladder slides down the wall at 2 feet per second, at what rate is the bottom of the ladder moving away from the wall when the bottom of the ladder is 10 feet away from the wall? So at this particular point in time, when the bottom of the ladder is 10 feet away from the wall, when x equals to 10, the bottom of the ladder is moving away from the wall at 4.8 feet per second. That's the value of dx dt. Okay, all right, hopefully this makes sense. But like I said, these are really hard work problems. They're all a little bit different. But what they have in common is that in every single case, you got to figure out what is the quantity we're dealing with. What are the rates, right? There'll be language about the rate or the speed or how fast is it changing or how does it change. So look for the keywords change or the keywords rate or speed or margin. So all those things indicate that there is a change in the variable. That means it's derivative. You got to come up with some sort of picture. You got to come up with some sort of picture that connects, some sort of an equation that connects all these variables. Pythagorean is a very popular one, but it could also be like a formula for area of a circle or the formula for the or the area of a triangle. A variety of different equations might be used. And next, we're going to have to use implicit differentiation to come up with a new equation that involves both the quantity variables as well as their derivatives. Next, there will be some way of solving for the derivative that they want. Well, I should correct that. They don't always want a derivative, but most of the time is what we need. Okay, so no two problems are identical. That's what makes this section really, really tough. However, there are a lot of similarities. Okay, so let's take a look at a general plan of attack that can help you with the questions in this section. Okay, read your question. Then step one, sketch a figure if helpful, right? Draw a little something. It doesn't have to be a great work of art, just the key points. You know, you can draw a dot to represent a plane or a little box to represent a car. Just something that just kind of describes the word problem. Identify all relevant variables, including those whose rates are given and those whose rates can be found. So be careful when you're reading it to distinguish between a quantity, like a distance, and the way that distance is changing, its speed. So look out for keywords like the speed, the rate, how it changes, the change in, the margin is another keyword for business questions. So keep that in mind. Express all the given rates and rates to be found as derivatives. Be careful with which derivative you want to, which variable you want to take the derivative of with respect to which variable. Time is often a very popular variable to use, but that's not always the case, so be careful. Again, experience will help with that. Find an equation connecting the variables identified in step 2. So that can be hard. So think about whether they end up creating a triangle or a circle, or if there's a relationship like profits and costs and revenue functions, those kinds of known equations. So come up with an equation. Then step 5, implicitly differentiate the equation found in step 4 using the chain rule where appropriate and substituting all the given values. Okay, and then finally solve for the derivative that will give you the unknown rate that you're looking for. Okay, so that's easier said than done. Like I said, every question is going to be a little bit different. So it just takes a little bit of practice and trying out different things. So let's try another one. Okay, suppose that at the moment a westbound plane traveling 120 knots is 120 nautical miles from an airport. A northbound plane traveling at 160 knots passes directly over the airport. How fast is the distance between the planes changing 1/2 hour later? Assume that the planes continue at the same speed and direction. Okay, so Your author provided this nice little graphic for it. So we have a westbound airplane. So this is the westbound airplane. So see the little arrow here, direction. So this is the westbound airplane. And then we have another airplane here heading northbound. So this is the northbound airplane. Northbound airplane going that way. And then these are the rates of change, right? This is a measurement of velocity for the airplane. 120 nautical miles per hour, knots, is the direction heading in this direction, heading westbound. So I'm going to draw my own picture because there's one more element to this, and that's time. So let's say I'm going to draw basically the same thing, but maybe not as much detail. At t equals to 0, when time equals to 0, then we have our airport here. I'm just going to call it LAX. And I have this westbound airplane over here. So here's this airplane, this westbound airplane, headed this way. So here it goes this way. At time 0, we know that this is 120 miles. Let's scoot over here so you can see it. 120 miles from the airport. Let's use W, the letter W, to represent the distance that this westbound airplane is away from the airport. Right? This is the westbound airplane. Okay, and then there is a speed associated with it. It's traveling at 120 knots. So that's the rate of change of W, right? How fast is W, the distance away from the airport, changing? So we have dW over dt is going to be the 120. However, we have to be careful about signs. So as time goes on, this airplane is going to be getting closer and closer and closer to LAX. Therefore, the distance W, that variable, is going to be getting smaller and smaller and smaller. It's decreasing. As time goes by, that variable is going to get smaller and smaller, which means that this derivative has to be negative. Okay. All right, now at time 0, we have this other airplane that happens to be right on top of the airport at that moment in time. So it's this airplane. This is an airplane. There's this airplane. Wow, that's really ugly, but, well, okay. It's an airplane. Okay, at time 0, there it is. It does have a certain velocity, but it's really hard to do anything with it because it's sitting right on top of the airport. So let's skip on forward because they also ask us about the distance changing 1/2 hour later. So let's scoot out a little bit more. And let me draw another scenario over here, because we have another case when LAX is here. And now a 1/2 hour later, this is when t equals to 1/2 hour later, then this northbound airplane has now traveled some distance. Again, this is supposed to be an airplane, whatever, goes that way. So northbound airplane, this is the northbound airplane. Now has traveled some distance, capital N, right? Northbound, capital N, and it has a velocity, a rate of change of this variable, and that's where this dn over dt is going to come in, and we're told that it's traveling at 160 knots. Good. And then we still have this other westbound airplane. So there's this westbound. Now it's a little closer though, because it's 1/2 hour later, it's been traveling. So now it's going to be a little bit closer. Again, this is my interpretation of a plane. Wow, that's maybe that way. I don't know. Whatever. This is the plane. Like that. So now there is some sort of distance there. W to be determined. It's not 120 anymore because it's a half hour later and this plane has been traveling. It's been getting closer. But there is a distance between the airplanes. Over here, it was kind of silly because the distance between the airplanes at this point would have been exactly the same as the distance right there, right? So the distance between the planes would have been the same as the distance between the westbound plane and the airport, which would have been 120 miles. But as we move forward, that's not going to be a constant. As we move forward in time, this airplane is going to continue to travel in this direction at a speed of dNdt equal to 160. Right, so it's traveling that way, and this one keeps traveling toward the airport, presumably stopping at the airport, or maybe it just keeps going right past it and keeps going west. We don't know. But the distance between them, this variable, is going to change. Now, we could use the letter d for distance. It seems pretty plausible. But then when we take derivatives, it's weird because we have d dt of d, so it looks pretty ugly. So we should look for a different variable. So I'm just going to use the letter a. We'll say a is that distance between the two airplanes. Good. So a equals to the distance. So let's label some of our variables to be sure of what all these things represent. So W represents a distance. Okay, so W represents the distance between the airport and the westbound plane at t equals to 0. We've established that W equals to 120. At t equals to 1/2, we've established that W equals to, oh, okay, well, we have to figure out what that is, right? It's going to be different. We'll figure that out in a second. So I'll just put it in a box right here. Yet to be determined. N represents the distance between the airport and this northbound plane. Okay, so again, at t equals to 0, n is equal to 0 because it's right over the airport. So it hasn't traveled anywhere. You know, the distance between the airplane and the airport is 0 at that point. And at t equals to 1/2, well, then it's traveled a little bit, so we'll have a value for n at that point, right? Again, to be determined. We'll figure that out in a second. We also have these derivatives running around. So we have dw dt, which is the speed or the velocity of the airplane, velocity of the westbound plane. And we have d capital N over dt, which represents the velocity of the northbound plane. And finally, we are interested in the distance change. How fast is the distance between the planes changing? So A is the distance, capital A is the distance between the planes. Capital A is the distance between the planes. And so then dA dt, d capital A, dt is exactly what we're interested in, the change in the distance between the planes. Okay, so we've established that we kind of have two different pictures going on. We have the case when time equals to 0, and then we have the case when time equals to 1/2 hour later. Now, the northbound plane is traveling at a fixed speed of 160 knots, 160 nautical miles per hour. So when t equals to 1/2, then n is going to be equal to 160 times 1/2. It's traveled, right? N is a distance. So if it's traveling 160 nautical miles per hour for half an hour, you're going to get a value of 80 nautical miles. 80 miles, nautical miles. And then likewise for W, we are traveling at a fixed speed of 120. So W is equal to, okay, you were 120 miles away at time equals to 0, and then you're chipping away at that because you're getting closer and closer and closer and closer to the airport, and you're getting closer at a speed of 120 nautical miles per hour. So if you had been traveling at this speed for 1 hour, well, you would be at the airport. But you didn't travel for 1 hour, you traveled for half an hour. So this would be W equals to 120 minus 60, which means W equals to 60 miles, 60 nautical miles. Okay, so that brings me back to this. Let's fill this out now. Let's get rid of this. Let's get rid of that. We're ready to write it down. So at t equals to 0, W is 120 miles. At time equals to 0, the westbound plane is 120 miles from the airport. At t equals to 1/2 hour, 1/2 hour later, W is now only 60 miles from the airport. Okay, likewise, the northbound airplane, when t equals to 0, n equals to 0, it's right over the airport, so it's 0 miles away from the airport. Half hour later, because the plane is traveling at a fixed speed of 160 knots, then the plane is going to be 80 miles from the airport. Okay, so what about the variable a? When t equals to 0, right, let's make some space here. When t equals to 0, then that's this case over here. Well, the distance between the airplanes is exactly the same as the distance between the airport and the westbound plane. So at t equals to 0, capital A equals to 120. What about at the case when t equals to 1/2? In this triangle, what's the distance, the value of A? Let's squeeze it into here. So we could use the Pythagorean theorem that n squared plus w squared equals to a squared. And we already know that the value of n is equal to 80. So 80 squared plus 60 squared must be equal to the a squared. So the square root, and it's plus or minus when we take the square root, of 80 squared plus 60 squared must be equal to a. And of course, we get to ignore the negative. Ignore the negative. So now we can just get our calculator out and figure out the value of a. So 80 squared plus 60 squared equal to 10,000. And then we want the square root of that. The square root of answer here is 100. Okay, so 1/2 hour later, A is going to be equal to 100 miles. Right? At this particular snapshot in time, the distance between the two airplanes is 100 miles. Right? 1/2 hour later, the two planes are 100 miles apart. However, that's not what they asked us for. They didn't ask us how far away are the two airplanes. They're asking us how fast is the distance between the planes changing. So they're asking us about dA dt, not A. That's a very common source of misunderstanding for people. Okay, so next we want to bring together all the variables into something. Oh, let's fill out this guy here. This was 60 there in this one, and so n equals to 80 in this one. Okay, and A we just established was equal to 100. So at this particular snapshot in time, these are the values of N, A, and W. So let's bring all those together again using our Pythagorean formula. Let's put it over here. And so we have N squared plus W squared equals to A squared. And now we're going to take a derivative with respect to t of everything. N squared plus W squared equals the derivative with respect to t of the A squared. Okay, so now using implicit differentiation, we can figure out that this is equal to 2 capital N dN dt plus 2W dW dt is equal to 2A dA dt. Okay, so we have a new formula here, and the advantage of this formula, the great thing about this formula is it contains the variable or the value of interest, the rate of interest. They asked us about dA dt, the speed with which the distance between the two planes is changing. So that's the one we want to know. And everything else we have. At this particular point in time, n, we said n is equal to 80. Dn dt, well, we have that. That's equal to 160. W, well, that's equal to 60. And dw dt, well, that's equal to negative 120. Did I put that somewhere? Oh, yeah, here it is. Negative 120. We established that the sign is important. And A, we established A was 100. So we have everything we need here to solve for this value, this rate. Okay, so let's make a little more room. So solving for dA dt, all I'm going to do is divide everything by 2a. So I'll get that dA dt is equal to this whole left side divided by 2a. So it's 2n dn dt plus 2w dw dt, all of that divided by 2 capital A. Okay, so now we've got every single one of these values. We can solve for our rate. So 2 times n, we said n is right here. It's equal to 80. Times dn dt. dn dt is equal to 160. Plus 2 times w, 2 times w, and the w we said was 60, times dw dt, and dw dt is negative 120. And all of that gets divided by 2 times a, which is equal to 100. Okay, we punch that into our calculator. Let me put that over here. That means that dA dt is going to be equal to 56. Okay, so this means that the distance between the planes is changing. It's increasing, right? Because it's positive. It's increasing at a rate of 56 knots. So let me box that up over here. So the distance between the planes is changing at a rate of 56 knots. Good, 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 good. Okay, so again, read your question, read it again, read it a third time, make sure you get a pretty good understanding of what they're describing. Start drawing pictures. Doesn't have to be a perfect picture, just something to kind of represent the various quantities in question. Start labeling your variables. I would describe the variables off somewhere because it's easy to forget whether W was supposed to be a distance, whether W was supposed to be a quantity, it could be a variety of things. So label them. make sure that you are clear if there are two different snapshots in time. So you might want to do more than one picture like the way I did here. There might be another word problem where they say something like 45 minutes into the flight, blank, 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 and then 3 hours later, blank, blank, blank. So you have two different snapshots of time. And so the same variable might have two different values at two different points in time. Right? So you might need different pictures. So keep those straight and keep those in mind. Usually, just sort of by practice, once I established my quantities and I established my variables, I know that I'm going to be interested in derivatives of those. Often it's with respect to time, especially if you're talking about, well, very often it's a very popular a very popular request in these types of problems to find the derivative with respect to time. So be careful which derivative you're asked to use. I try and figure it out based on what information they've given me. So I knew that this involved a derivative with respect to time because they gave me a speed, a velocity, right? So that automatically lets me know that's what I'm dealing with. Okay, and then some people jump to setting up the equation and then kind of reverse engineer it and think about all the things they're going to need. They're going to need an n, they're going to need a dn dt, they're going to need a w, they're going to need all these things, and then they kind of go back and find them. So it just depends on your style, and every word problem is a little bit different. So you'll develop your own kind of systematic approach. Just try and be neat. I know this is pretty messy as well. I'm still getting used to this method, this working with this software program here. If we were in an in-classroom setting, I think I'd do a better job of organizing my board work and putting it all nice and neat on the board. But this isn't too bad. Okay, all right. Hopefully this one makes sense. Let's move on to another one. Okay, suppose a point is moving in a circular path centered at the origin and radius 5. The graph has the equation x squared plus y squared equals to 25. When the point is located at -3, 4, so that's in quadrant 2 somewhere, its x-coordinate is increasing at a rate of 0.4 units per second. How fast is the y-coordinate changing at that moment? Okay, so let's start by doing a little picture. So here's a nice graphic your author provided. Okay, so we have a nice circle centered at the origin. The radius is 5 units. Let's put it in here, put it in green. So we know that the radius from here to any point on that circle, the radius r, equals to 5. And so any point on that circle, and that circumference, is going to obey this rule, right? This is the equation of a circle, x squared plus y squared equals to 25. So here is a particular point. We can confirm that that's a point on this line. Let's confirm it. So let's see, if we plug in blank squared plus blank squared equals 25, and so if we let x equal to -3 and y equal to 4, we get -3 and 4. That makes it a 9 plus 16 equals 25. Yep, that's true, right? So any point that's on this curve, any value a comma b that's on this circle must satisfy the equation, right? That's what this formula represents. Okay, when the point is located at -3, 4, so you're in quadrant 2, you're right here, its x-coordinate is increasing at a rate of 0.4 units per second. How fast is the y-coordinate changing at that moment? Okay, again, they've given us a change, a speed. It's increasing at a rate of 0.4 units per second, right? So we know it's over time. So they've given us the x-coordinate, that's -3. They've given us the y-coordinate, that's equal to 4. And they've given us dx dt.
the way that the x variable is changing, and that's equal to positive 0.4. So we have these three things, and what they're asking for is how the y-coordinate is changing. So I know that it's dy dt that they're interested, right? That's the question mark. This one's going to be an easy one, way easier than the one before. So if we have x squared plus y squared equals to 25, let's take a derivative with respect to t, right, inspired by the information they've given me and the information that they asked for. Let's take the derivative d dt of x squared plus y squared, and then on the other side, the derivative with respect to t of 25. Well, that's going to be easy. This is a 0. So this is going to be equal to 2x dx dt plus 2y dy dt equals to 0. And so this is the variable of interest. We can divide everything by 2. Divide this side by 2, divide that side by 2. And so it'll cancel here, right? Factoring those guys. And so, let's bring this over here. We have x dx dt plus y dy dt equals to 0. Remember, 0 divided by 2 is still 0. And we're interested in this variable, so let's solve for it. Moving this term to the other side, we get y dy dt is equal to minus x dx dt. And now if we divide everything by the y, we'll get what we want. dy dt is equal to negative x dx dt divided by y. Good. Okay, so we have everything we need. Let's plug it all in. We get that x is negative 3, so we have a minus from out here, and then the x itself is also a negative, so we're going to have a minus there and a minus there. dx dt, that's equal to the 0.4 divided by the y, and the y was a 4. So now if we multiply that all together, we should get that this is equal to 0.3. Okay. So bring it together, the dy dt equals to 0.3 units per second. So the y-coordinate is increasing. So when the point, put a full sentence here, when the point is located at negative 3 comma 4, the x-coordinate is increasing at the rate of 0.4 units per second. That was given. I haven't found, that's nothing new. And then the part I'm going to contribute is that at the same time, when the point is located at the point negative 3 comma 4, so this is the part we found, the y-coordinate is also increasing at a rate of 0.3 units per second. Right? And I knew it was increasing because it's a positive value. Remember, the sign makes a difference. If all of this turned out to be negative 0.3, then I know that it would be decreasing at that moment. Okay, so read your question, draw a picture, come up with an equation that connects the variables, the quantities of interest. Sometimes that's really obvious, like it is here in terms of the circle. But it might be a question that involves the area of the circle instead, or it might be a question that involves the circumference of the circle, the distance traveled by a point going in a circular direction. It could be a variety of things. So you have to be careful. Every question is going to be just a little bit different, and that's why this section is really challenging. Okay, let's do one more example that involves business things, since you guys like business questions, right? Okay, let's try this question out. Suppose a company manufacturing flash drives determines that their cost, revenue, and profit equations are given by these. So the cost function is equal to 5,000 plus 2x. Okay, so there's a fixed cost of $5,000 plus twice x, and this is where X represents where the product output in 1 week is X flash drives. So it's the number of flash drives produced in 1 week. Okay, so it's $2 per flash drive plus $5,000 is their cost equation. Their revenue equation is 10x minus 0.001x squared. Okay, so you plug in the number of flash drives produced in a week, and that will help you figure out the revenue. And then finally, profit is equal to revenue minus cost. Okay, the great thing about these questions involving applications of business is that the formulas, should be really familiar to us, and they're often given, or they're, relatively easy to find. So from that perspective, these questions should be a little bit easier. So part A, if production increases at a rate of 500 flash drives per week when the production is 200 flash drives, find the rate of increase in cost. Okay, so production increases when the production is, so the production value, well, that's just going to be X, right? So this is saying, let's put it in. This right here is saying that X must be 2,000. Right, so we're producing 2,000 flash drives a week, 2,000 flash drives per week. And now if the production increases at the rate of 500 flash drives per week, okay, so that would be a derivative of the X variable, right? A change in the X variable. So in a week's time, so this is kind of the velocity of the production. So this is going to be that dx dt equals to 500. Now remember, the sign is important, so pay attention to it. And we're saying that it's increasing, it's going up, right? So this variable is going to be on its way up, so this is a positive. If it had said that the production is being slowed, it's decreasing, it's smaller, any of those would be a hint that this is getting smaller over time, which would mean that this would be a negative. Okay, so if production increases at a rate of 500 flash drives per week when production is 2,000 flash drives, find the rate of increase in cost. Okay, so that would mean that for part A, we're interested in this formula. So let's come back over here. I'm going to box off this whole thing here and say for part A, I'm interested in the cost function. So cost equals to, and it's the cost function, but it's a function of x, right? So another thing you could do is rewrite this as c of x equals to 5,000 plus 2x. And we're interested in the derivative of this guy. So it's ddc derivative with respect to time of the cost function is equal to the derivative with respect to time of 5,000 plus 2x. So that means that dc dt is equal to, so the derivative with respect to t of 5,000 plus the derivative with respect to t of the 2x, right? Again, the variables don't match. So this is going to mean that dc dt is equal to 2 times dx dt, which we know dx dt is 500. So dc dt is equal to 2 times 500, which means that it's equal to 1,000. Right? So that's our answer. Cost is increasing at a rate of $1,000 per week. Okay, part B. If production increases at a rate of 500 flash drives per week when production is 2,000, so that's the same variables right here. Let me just go ahead and erase this. Okay, find the rate of increase of revenue. Okay, so then we are interested in the rate of change of the revenue function. So we have r, or r of x, right? It's a function of x. R of x equals to 10x minus 0.001x squared. And so we're interested in the derivative with respect to time of the r function. And that's equal to the derivative with respect to time of 10x minus 0.001x squared. And so that gives us dr dt equals to 10 times dx dt minus 0.001 times 2x times dx dt. Good. And we have everything we need. dx dt is 500 and x is 2000. So dr dt is equal to 10 times 500 minus 0.00, okay, if I just multiply those, it would be a 2 there, 002, times the x, which we said was 2000, 2, 3, times dx dt, which is 500. Okay, so that means that dr dt is equal to so this is going to be 10 times 500 minus, and let's put that in parentheses, 0.122 times 2000, 2, 3, times 500, 100, close parentheses, equals to 3000. So we have that dr dt is going to be equal to, well, this is going to be 5,000 minus, and this is going to end up being 2,000. So dr dt equals to 3,000. Okay, so this means that the revenue is increasing. I know it's increasing because it's positive. It's increasing at a rate of $3,000 per week. Right? So in this scenario, here is our cost function, our revenue function, our profit is, of course, is equal to the revenue minus the cost. And when we are producing 2,000 flash drives per week, and we are changing, the change in the production is changing to 500, or it's changing by 500 per week, then at that point, our cost is increasing because we're producing more. So it's increasing by $1,000 per week. However, our revenue function is also increasing. It's increasing by $3,000 a week. So finally, part C, if the production increases at the rate of 500 flash drives per week when the production is 2,000 flash drives, find the rate of increase of the profit. Okay, so now for part C, let's look at our profit. So part C, we'll squeeze it in down here. So we have that our profit is equal to R minus C, the revenue minus the cost. So if we take the derivative with respect to T of the P, and then take the derivative with respect to T of this R minus C, we end up with the formula dP dt is equal to dr dt minus dc over dt. And so this is the one we're interested in, and these two we just found. dr dt is right here. Here is dr dt. And right over here we have dc dt. dc dt is equal to 1,000. So from that we can conclude that dp dt is equal to 3,000 minus 1,000, or that dp dt is equal to 2,000. Okay, so what does that mean? That means that our profit is increasing. Again, it's positive, increasing at a rate of $2,000 per week. Okay, let's recap real quick then. So we have a cost function up here, 5,000 plus 2x. We have a revenue equation, revenue R equals to 10x minus 0.001x squared. And then, of course, we know that the relationship between cost and revenue and profit is equal to this. The profit equals to the revenue minus the cost. Okay, in all three cases, we were asked to consider the case when the production level was X equals to 2,000 flash drives being produced per week, and that the change in production, we're increasing the rate in production by 500 units per week. So consider how that impacts the way the cost is changing, the way the revenue is changing, and the way that the profit is changing per week when we implement this change, or as we're implementing this change. Okay, so for each one of these, we really just have to take the derivative with respect to t of each one of these functions and then plug in the values we have. So it's really a pretty straightforward question. So we found that at this point, when the production level is 2,000 and the production is increasing at a rate of 500 units, the cost is increasing at a rate of $1,000 per week. Makes sense? We're producing more, so our cost is going to go up. Our revenue is also going to increase. We found that the revenue is going to be increasing by $3,000 per week. And if we just look at our profit, revenue, and cost relationships, it would make absolute sense that if the cost is going up by 1,000, but our revenue, the money coming in, is going up by 3,000, then the profit is going up by 2,000 per week. Good. Okay, so hopefully this is enough to get you started on these questions. Please don't hesitate to come to my office hours if you have any questions about any of these guys.